Now, we discuss a geometric meaning for the orthogonality relations of the characters. Consider an irreducible representation gamma alpha of the group, and for each class Ck of the group, the character of that class in this representation will be denoted by chi alpha k. Now we can collect the characters of each class and construct a c-dimensional vector named chi alpha in the following way. So take chi1 alpha, the character of class C1 in this representation, multiply it with square root of n1, which is where n1 is the number of elements in class C1. Then the next entry here would be chi2 alpha square root of n2 and so on up to chi c alpha square root of nc, where c is the number of classes of the group. And this can be considered as a vector in a c-dimensional complex vector space, and we call it as chi alpha. Now these vectors will be called character vectors, and the space in which these vectors live are called the class space, is called the class space. Now we can define an inner product in this space in the following way. So the inner product chi alpha chi beta is simply just as we did before, a dot b or a comma b inner product was defined as sum over I, ai star bi. We can do the same thing over here. So when we do that, the summation is over these elements, and we use a summation index k here, k running from 1 to c because there are c elements. Then the complex conjugate of the elements of chi alpha, so that will be written as the complex conjugate of chi1 alpha square root of n1 multiplied by the corresponding chi k alpha star square root of nk. Then the corresponding element of chi beta would be chi k beta square root of nk. So chi k alpha square root of nk star, but since nk and square root of nk are real, we can apply the complex conjugate here only, times the one corresponding to this, that will be chi beta k again square root of nk. But square root of nk times square root of nk is nk. So the inner product defined this way would be simply sum over k running from 1 to c chi k alpha star chi k beta times nk. But the first orthogonality relation for classes that we discussed earlier says that this is simply equal to g times delta alpha beta. So that means if alpha beta and beta are two inequivalent irreducible representations, then this inner product is 0. Or in other words, if we are considering inequivalent irreducible representations and the vectors corresponding to them, these vectors are all orthogonal to each other. They are mutually orthogonal, and therefore they are linearly independent. And we just need to find how many such vectors are there. There will be one such vector for each irreducible representation. And if the number of irreducible representations is denoted by R, the number of vectors chi alpha is also R. And these R vectors are linearly independent. And the dimensionality of the space of these vectors is simply C. Now, as we know, the number of linearly independent vectors cannot be greater than the dimension of the space, and therefore the number of linearly independent vectors that we just counted here is R, and that should be less than or equal to the dimensionality of the space, which is C. So we get the first inequality connecting R and C, where R is the number of irreducible representations and C is the number of classes of the group. Now we also had another orthogonality relationship among the characters, and which was that sum over p chi p alpha star times chi q alpha is equal to, and sum over alpha running from 1 to r, and this product, this sum is equal to g by np times delta pq. And to make use of this, we will construct character vectors in the following way. So given a particular class ck, we consider all the irreducible representations of the group, which are denoted by alpha, gamma, alpha, and the character in that irreducible representation of the class ck is represented by chi alpha k, and we collect the characters of the class ck in each of these irreducible representations in this form. So we will have chi k1, chi k2, and so on up to chi kr, where r is a number of irreducible representations of the group. And together it is denoted by chi k and can be considered as a vector in an r-dimensional complex vector space. As we did earlier, we can construct an inner product here as an inner product between chi p and chi q. This one corresponding to the class Cp and this one corresponding to the class Cq, and their inner product can be written as sum over alpha running from 1 to r, chi p alpha star chi q alpha. But we already know from the orthogonality relations of these characters that this is equal to g divided by np times delta pq. So when p is not equal to q, that is for two different classes, this inner product is 0. So that means these vectors chi k are orthogonal, mutually orthogonal, and therefore they are all linearly independent, and there is one such vector for each class, and therefore the total number of linearly independent classes of this type is simply C, which is the number of classes. Now the dimensionality of the space is R, the number of irreducible representations. The number of linearly independent vectors should be less than or equal to the dimensionality of the space, and therefore C should be less than or equal to R. We earlier got another inequality, that was this one. It says that R should be less than or equal to C, and we now have this inequality also. And both these inequalities can be satisfied only if R is equal to C. So that immediately gives us a very important result, which says that the number of irreducible representations of a group is simply equal to, of a finite group is simply equal to the number of classes of that group, number of conjugacy classes of that group.